Hey everyone, and welcome to Explainer. Today, we are unpacking something absolutely groundbreaking in the world of medical AI. We're looking at a brand new architecture that's designed to make AI agents reliable enough to handle incredibly complex, multi-step MRI workflows from start to finish. If you've ever wondered how we get an AI to stop acting like a basic chatbot and start functioning like a totally dependable, multi-stage medical research assistant, well, you're in exactly the right place.
Here's our roadmap for today. We'll start with the MRI AI problem, meet the BCER Agent, break down its anatomy, walk through a real cardiac case study, dive into the benchmark results, and finally look at the future of medical AI.
But before we really get into the weeds here, I want you to picture something. Imagine a highly advanced AI system, right? It's tasked with analyzing this incredibly complex 3D volumetric brain scan. It successfully nails the first 3 steps of the analysis, and then, out of nowhere, it hallucinates a file path. It literally just loses track of the physical data halfway through its pipeline. So what happens? The entire workflow collapses. The stakes here are incredibly high, and honestly, this exact scenario is what researchers are trying so desperately to prevent.
Part 1. The MRI AI problem. Moving beyond short interactions.
You see, a lot of today's medical AI agents are evaluated on what we call short tool calling exchanges. Think of basic visual Q&A on a single, flat 2D slice of an MRI. But real-world MRI analysis just isn't like that. It naturally demands long-horizon workflows. We're dealing with massive 3D and even 4D volumetric data. And that fourth dimension is time, like imaging a beating heart over a full cardiac cycle. That exponentially increases the data load and creates these multi-stage, highly dependent pipelines. You've got to ingest the raw data, reconstruct it, pre-process it, segment it, extract features, and then finally synthesize a report. It's like a giant chain, and if one single link breaks, the whole thing falls apart.
The researchers hit the nail on the head with this quote. They point out that reactive tool-calling agents, which is the standard setup we use today, are prone to cascading breakdowns triggered by faulty intermediate references, mismatched tool arguments, and limited control over cross-step dependencies. So, in plain English, standard AI models try to think and act at the exact same time, which inevitably leads to sloppy mistakes in long workflows. We desperately need a new architecture.
Which brings us to Part 2. Meet the BCER Agent, Bounded Execution and Recovery.
Enter our hero, the BCER Agent. BCER stands for Brain-Cerebellum-Extremity-Reflector. And I just love this. The researchers used a brilliant biological metaphor to name their system. Think about the human body. Your conscious brain doesn't tell your individual muscle fibers exactly how to contract when you're walking, right? It relies on the cerebellum to coordinate those granular details and your extremities to actually execute them. And if you stub your toe, a local reflex, a reflector, handles that immediate pain response without you having to relearn how to walk. This AI architecture uses that exact same philosophy, cleanly separating high-level thought from physical action and local healing.
Part 3. Anatomy of the solution. Decoupling planning from execution.
It's so fascinating how clearly this biological metaphor maps to the computing pipeline. Right at the top, you have the brain producing a constrained plan sketch. It's not writing executable code, it's just plotting the course. Then, in the middle, the cerebellum takes that abstract sketch and does something absolutely vital. It compiles it using a directed acyclic graph, or DAG compiler. This literally turns those abstract ideas into a rigid, physically executable workflow graph. At the same time, the cerebellum enforces a case scope guard, locking down the data to ensure strict patient privacy during runtime. Down below, the extremities are the actual MRI tools doing the heavy lifting, data ingestion, pre-processing, analysis. And off to the side, the reflector stands guard, ready to execute active reflexes and self-healing if an extremity runs into an error.
To break that down just a bit more, the brain provides declarative planning and global horizon awareness. It always knows the ultimate goal. The cerebellum is the crucial bridge, compiling the plan and managing runtime execution. The extremity is a standardized MRI tool library that uses uniform arguments so everything fits together seamlessly. And the reflector ensures that if one step fails, the system performs bounded local repair. Now, this concept of being bounded is huge. Without it, a standard AI might try to fix a broken segmentation tool by hallucinating an entire rewrite of its underlying codebase. The reflector, though, just fixes the immediate input or output error, saving time and keeping the entire massive pipeline from completely resetting. So the real magic is how the cerebellum actually manages the data between these steps.
And it does this through a real game changer called symbolic artifact binding. Standard AI agents try to directly pass long, complicated file paths between tools, which often leads to the AI completely hallucinating a directory that doesn't even exist. But with symbolic binding, the AI just uses an abstract reference, like an @sequence token. The cerebellum then resolves that token to the concrete physical MRI file on the back end. This guarantees the tools are consuming real physical artifacts, completely eliminating a massive source of AI errors.
Section 4. A cardiac case study, taking us from raw data to a final report.
Let's look at this in action with a complete end-to-end cardiac workflow. The user's goal here is to process raw, multi-coil cardiac cine case-based data and determine a disease phenotype. You can trace the journey vertically. The top layer shows the brain's plan. The second layer shows those symbolic artifact bindings we just talked about, linking the steps together. The third layer is the actual physical execution by the extremities, transforming raw, blurry case space into a crisp 4D reconstructed MRI, overlaying a segmentation mask on the ventricles, and extracting metrics. And if we look closely at the generated report snippet, we see exactly what the system found. It successfully segmented the left and right ventricles, calculated a left ventricular end diastolic volume of 219.9 milliliters, and recorded a severely reduced ejection fraction of exactly 29%. By applying strict rule traces to those metrics, the AI outputs a final, highly accurate classification of dilated cardiomyopathy.
And just notice how deeply interconnected these steps actually are. Identify the sequence, reconstruct the 4D image, segment the ventricles, extract those quantitative features like the ejection fraction, and synthesize the final report. If the segmentation fails, feature extraction has absolutely zero data. If feature extraction fails, the report is blank. Every single step is vital, and BCR keeps the chain unbroken.
Part 5. The benchmark results. Measuring task success and completion.
Okay, this data is absolutely wild. It's nothing short of a revelation. The researchers compared BCR to a standard reactive AI, known as REACT, measuring success rate, meaning flawless completion, and task completion rate, which measures how many milestones were hit. Look at the bottom two rows, the long horizon tasks for prostate and cardiac reporting. The standard REACT architecture completely fails, 0% success rate. It literally cannot hold the pipeline together. But check out the intermediate steps, specifically the REACT plus bind column. Simply adding that symbolic binding mechanism caused the cardiac task completion rate to jump from 0 all the way to 63 out of 66. That single change proves how crucial it is to bind tools to physical artifacts rather than text strings. Then, moving to the far right column, adding the full BCR architecture pushes that cardiac success rate to 93 out of 93 and hits a 99% success rate on the prostate report. I mean, that is a night and day difference in reliability.
Now, to figure out exactly why this works so well, the researchers did an ablation study, essentially adding one component at a time. They found that just adding the bind mechanism dramatically reduced low-level reference errors. Adding the reflector fixed midstream execution crashes through localized healing. But you really needed the full BCER stack, especially the brain and cerebellum, cleanly separating planning from execution to fix structural workflow omissions entirely. A structural workflow omission is when the AI literally forgets the overarching plan and skips a critical step entirely, like bypassing segmentation and trying to write a report with zero data. The cerebellum's DAG compiler completely prevents that from happening. Every single organ in this artificial anatomy plays an indispensable role. Now you might be thinking, hey, is this just because they used a massively powerful underlying AI model? Well, the answer is a hard no, and this chart proves it. The researchers tested this architecture across major foundational models, QN3, OpenAI's GPT models, and Google's Gemini. Over on the right side, under long chain, you can see that the dark blue bars representing the full BCR architecture consistently hit near 100% success across all three totally different AI backbones. Meanwhile, those red bars representing standard reactive agents collapse under the weight of long tasks, completely regardless of the model used. Throwing a smarter, more massive language model at the problem just doesn't work if it doesn't have the right architecture. Even a behemoth model like Gemini gets completely lost in long horizon tasks if it doesn't have a cerebellum to separate its planning from its execution. The architecture is what guarantees completion.
Finally, Part 6. The future of medical AI. Trust through traceability.
Why does all this architectural success actually matter? Well, in a word, auditability. In clinical practice, you cannot just hand the doctor a final AI report and say, "Trust me." A doctor has to verify.
BCR's greatest gift to clinical practice isn't just its high success rate, it's the fact that it maintains explicit, unbreakable links between the final diagnostic conclusion and every single intermediate artifact and measurement. If the report says a patient has an elevated left ventricular volume, the doctor can literally click a link and immediately see the exact 3D segmentation mask the AI used to calculate that number. Trust is built through complete traceability.
So, this leaves us with a pretty profound realization. We are moving past the era of AI as a simple chatbot that just spits out text answers and entering the era of AI as a dependable, multi-stage medical orchestrator. As these agents gain the ability to flawlessly execute massive, interdependent medical workflows with total auditability, the question really is no longer, can AI do this? The question becomes, how will our healthcare systems adapt to actually integrate these deeply auditable digital assistants into everyday patient care? Thank you so much for joining me on this explainer. I hope this breakdown of the BCER agent was as fascinating to you as it was to me. Keep learning, and I'll see you next time.